Welcome, brothers. Let's get right into it. Today we're walking through a step-by-step explainer on exactly how we properly calibrate an ORP probe for our reverse osmosis systems. If you're an engineer installing and operating ultra-pure water filtration systems, you already know that keeping our polyamide membranes totally safe from oxidation is literally priority number one. So grab your notebooks. We are turning our comprehensive technical guidelines into a clear, accessible masterclass. I've broken this entire process down into 6 standard operating phases. We'll quickly cover the intro to ORP probes, move into preparation and inspection, walk through the actual calibration process, handle verification and reinstallation, touch on SCADA and documentation, and wrap up with a troubleshooting guide. All right, phase 1. Let's look at what these ORP probes are actually doing for us. As you know, we always position this probe right before the RO inlet. Usually that's directly after the carbon dechlorinator or right after the SMBS dosing point. Its one and only job is to guarantee our water has absolutely zero residual chlorine that could destroy that expensive polyamide membrane. It's measuring the oxidation reduction potential in millivolts. Basically, it's measuring the potential difference between a platinum sensing ring and, most commonly, a silver and silver chloride reference electrode. But before you even start, brothers, you've got to make sure your prep is perfect. Get your proper PPE on. That means a white lab coat, safety glasses, and blue nitrile gloves. Grab your Amberzol solution, and hey, always check that expiry date, right? You're also going to need some clean glass speakers, lint-free wipes, a DI water wash bottle, your calibration log form, and of course, a recently calibrated handheld ORP meter so we can cross-reference everything later. Moving right along to phase 2, preparation and inspection. Okay, I want you to get a really bright light and look closely at that platinum ring. It has to be shiny and metallic. It absolutely cannot be dull, black, or coated with any weird oil, protein, or tar. While you're at it, take a good look at the ceramic reference junction to make sure it isn't dried out or clogged up. Now, if you do find that the platinum surface is gunked up, you'll need to soak it in a 1 molar hydrochloric acid solution for about 15 to 30 minutes. But listen, this is absolutely critical. Never, ever use sandpaper or any sharp object on that platinum surface. You'll ruin it. Just check that your cable connectors are totally dry and free of any oxidation, and then always finish your prep with a really thorough DI water rinse. You know, the environment is a huge factor here, brothers. ORP readings are incredibly temperature dependent. You absolutely must record your standard solution's temperature. If your transmitter happens to use a P10 or P1000 temperature sensor, make sure you go into the menu and turn on automatic temperature compensation, or ATC. If you don't have ATC, well, you're going to have to manually look up your target millivolt value based on the actual room temperature. So, phase 3. Let's get into the actual calibration process. First up, rinse the probe with DI water and gently dab it dry with a lint-free wipe. And I mean dab, do not rub it. Then, submerge your probe into the Amberzol solution. You want to make sure both the platinum ring and the reference junction are completely covered. Give it a gentle shake to knock off any bubbles, and then just wait. It usually takes about 60 to 90 seconds until the reading stabilizes within a tight 2 millivolt range for at least 30 continuous seconds. Once it's completely stable, you're going to enter the offset calibration mode on your transmitter. This is where you input the theoretical value. So for a silver/silver chloride reference, Zobel is typically plus 228 millivolts right at 25 degrees Celsius. Enter that into the transmitter and hit confirm. The transmitter is going to calculate the offset adjustment. Now that offset adjustment absolutely must fall within plus or minus 10 millivolts. Quick side note, if your specific system uses a standard hydrogen electrode reference instead, your target is actually going to be plus 430 millivolts. So always verify your reference type first. Now, as an optional second step, but one I really recommend for a more rigorous check, you can rinse the probe and check the span linearity in a second solution. You might use light solution, which sits around plus 475 millivolts, or maybe a quinhydron saturated pH4 buffer, which is about plus 264 millivolts. What you're looking for here is a variance of less than 15 to 20 millivolts from your theoretical target. If it fails this check, your platinum surface is likely poisoned. All right, phase 4, verification and reinstallation. I highly recommend doing an independent cross-check here. Rinse the probe with DI water one more time and just put it right back into the Zobel solution. You want to verify that the reading is still sitting within plus or minus 5 millivolts of your target. This just confirms your calibration is actually repeatable and stable. After that, give it a final, thorough DI water rinse before you take it back out to the housing. Time to reinstall the probe securely into the stainless steel pipe T. Make sure your O-ring isn't torn, check for any leaks, and make sure there are no dead legs in the flow. Let the process flow resume and stabilize for a good 5 to 10 minutes. Once it's settled, pull a sample from the local sampling valve right next to the probe and immediately compare your online transmitter reading against your freshly calibrated handheld meter. So here is the absolute crucial point, guys. Your normal operating ORP must stay below positive 200 millivolts, or, whatever your specific plant design set point happens to be. Seeing this consistently low reading confirms complete chlorine removal right at the RO inlet. Also, keep an eye on the deviation between your inline transmitter and your handheld meter. That difference must be less than 15 millivolts.
Let's move into Phase 5, SCADA and documentation. Out in the field, you need to verify that the 4 to 20 milliamp loop actually matches the SCADA display in the control room. For example, if your range is minus 1,000 to plus 1,000 millivolts, a 0 millivolt reading should output exactly 12 milliamps. Next, make sure you firmly set your SCADA high alarm. Typically, we put this at plus 250 millivolts. If that alarm triggers, it's instantly warning us of a chlorine breakthrough. That means a technician needs to immediately get out there and check the carbon filter or the SMBS dosing pump. Just to summarize your strict pass-fail criteria, brothers, your offset adjustment has to be within 10 millivolts, your span variance within 20 millivolts, and that handheld verification has to be within 15 millivolts. If your deviation exceeds any of these limits, stop. You must re-evaluate the probe, check for ground loops, or thoroughly inspect the cable. Finally, it's paperwork time. Fill out every single line of your calibration form. I mean everything. Record the lot numbers, the theoretical millivolts, the offset adjustment, and the handheld verification numbers. Check that pass box and sign your name. Make sure your standard solutions are capped super tight and stored away from direct light. Then, set a reminder for your next calibration. Usually that's in 1 to 3 months, keeping in mind that these electrodes generally need a full replacement every 12 to 24 months, depending on how tough your plant's conditions are. And if things go wrong, we move to Phase 6. Our troubleshooting guide. Listen, things will go sideways eventually. If you start seeing drifting readings or notice a blackened platinum ring, which is usually caused by sulfide poisoning or organic adsorption, your very first line of defense is cleaning that reference junction or performing that 15 to 30 minute soak in 1 molar hydrochloric acid. If the response time is just incredibly slow, the junction might just be dry and needs to be rehydrated in potassium chloride or DI water. And if your reading is just wildly fluctuating around 0, you've probably got a broken cable or an oxidized connector on your hands. I want to bring this temperature point back up because it is without a doubt the most common mistake made on the floor. Always, always remember to use your temperature compensation chart if your equipment doesn't have automatic temperature compensation. Just look at the variance. At 0 degrees Celsius, Zobel is plus 236 millivolts. But at 40 degrees, your target drops all the way to plus 223 millivolts. If you don't account for temperature, your offset is going to be inherently flawed, and you are literally putting the entire RO membrane at risk. Protecting an ultra-pure water system takes total vigilance, crazy precision, and a real commitment to the standard operating procedures we've just laid out today. So I want to leave you with one critical question. Are your standard solutions properly dated, unexpired, and securely stored for your very next calibration? Make sure you are fully prepared the next time you step onto the floor to protect our RO systems. Keep learning, stay precise out there, and I'll catch you in the next explainer.